Hello students, in this lecture we will study Gunn diode. Definition of Gunn diode. Gunn diode is a transferred electronic device which is composed of only one type of a semiconductor, that is a N type, and utilizes negative resistance characteristics to generate current at high frequencies. It is used to generate RF and microwave frequencies. So this is in this Gunn diode, it utilizes negative resistance characteristics, or Gunn diode operates in a negative resistance. So in objective type questions, such type of a question is asked. That is it is operates in a negative resistance. So Gunn effect, that is Gunn diode operates on this Gunn effect and are named after J.B. Gunn, who in 1963 discovered a periodic fluctuations of a current passing through then type, that is a gallium arsenide specimen, when applied voltage exceeded a certain critical value. So this Gunn diode is developed or introduced by first J.B. Gunn in 1963, and he has explained Gunn effect, then Gunn diode symbol. So this is symbolic representation of Gunn diode, and it is generally composed of N-type semiconductor, because N-type semiconductor has electrons as a majority carriers, and transferred electronic devices uses such materials which have electrons as a majority charge carriers. Okay, for such devices the p-type semiconductor is of no use because it consists of holes as a majority carriers. Therefore Gunn diode is made up of only N-type semiconductor, not a p-type. So in this Gunn diode only p-type, only N-type semiconductor material is used, and this symbolic representation is as shown in this diagram. Construction of a Gunn diode. So as previously mentioned, it consists of only N-type material as shown in this diagram, N plus N, N, and this is a heat sink, and this is an anode, this is a cathode. Then material use, that is it is made up of three layers of a N-type semiconductor as shown in this diagram, and semiconductors used in Gunn diodes are gallium arsenide, gallium nitride, cadmium telluride, that is CDT, cadmium sulfide, indium phosphide, indium arsenide, indium antimonide, and zinc selenide. But basically, in most of the Gunn diodes, this gallium arsenide material, GaAs material, is preferred. Among these three layers, the topmost and bottommost are heavily doped, while middle layer is lightly doped. So this topmost layers is heavily doped and middle layer is lightly doped in comparison to the extreme layers. The middle layer is an epitaxial layer grown on N-type substrate, and the topmost layer is formed by ion implementation technique. The metallic contacts are provided to extreme layers to facilitate biasing, and the heat sink is there so that diode can withstand excessive heat and can be prevented from damage. So these are heat sink is provided, and as this is a constructional explanation of a Gunn diode. So this is another diagram of a diagrammatical representation of a Gunn diode. This is a cathode, anode, and this length is 100 micrometer, and this length is a 75 micrometer, and vertical height is 120 micrometer. Then this Gunn diode operates on Gunn effect. So what is Gunn effect? In semiconductor materials like gallium arsenide, the electrons are present in high mass, low velocity state, and low mass, but high velocity state. By the application of sufficient electric field, these low mass, high velocity state electrons are forced towards high mass state. At this particular state, electrons form a cluster and thus moves at a uniform rate, thus causing a flow of current in the form of series of pulses. And this is termed as a Gunn effect and is utilized by Gunn diodes, hence named so. Okay, so why this name given? That is in semiconductor materials like gallium arsenide, the electrons are present in high mass low velocity state and low mass but a high velocity state. By application of sufficient electric field, these low mass high velocity state electrons are forced towards the high mass state, and during this current is a, or flow of current is there. And as previously mentioned, Gunn effect is the basis of working of Gunn diode. It was discovered by, as previously mentioned, physicist J.B. Gunn in 1963. So in J.B. Gunn, in his research paper, he has expressed following points, that is above some critical voltage corresponding to an electric field of 2000 to 4000 volts per centimeter, the current in every specimen become a fluctuating function of a time. In the gallium arsenide specimens, these fluctuations took the form of a periodic oscillation superimposed upon the pulse current. The frequency of oscillation was determined mainly by the specimen and not by external circuit. The period of oscillation was usually inversely proportional to the specimen length and closely equal to the transit time of electrons between the electrodes, calculated from their esteemed velocity of slightly over 107 centimeter per second. So Gunn effect expressed these points in his research. In VI characteristics, we will study when voltage is applied, then current increases up to peak value, and as current is produced there, we'll study those VI characteristics. In that, this Gunn effect will explain in detail. So this is another diagrammatical explanation, that is from Gunn's observation, the carrier drift velocity is linearly increased from 0 to maximum. This is a drift velocity and this is electric field. This carrier drift velocity is linearly increased from 0 to maximum when electric field is varied from 0 to threshold value. So this is a threshold value. When the electric field is beyond threshold value of 3000 volt per centimeter for the n-type gallium arsenide, the drift velocity is decreased from this threshold value. This drift velocity is decreased and diode exhibits the negative resistance. Okay, so this diode exhibits the negative resistance, and how this exhibits the negative resistance we can explain in VI characteristics. The current fluctuations are shown in this diagram. As current is produced there, the current waveform was produced by applying voltage pulse of 16 volt amplitude and 10 nanosecond duration to a specimen of a n-type gallium arsenide of a 2.5 by 10 centimeter in length. The oscillation frequency was 4.5 GHz. Gunn found that the period of these oscillations was equal to the transit time of the electrons through the specimen, calculated from the threshold current. So next, working principle of a Gunn diode. This diode is made up of a single piece of a n-type semiconductor such as gallium arsenide and indium phosphide, as previously mentioned. GAS and some other semiconductor materials have one extra energy band in their electronic band structure. Instead of having only two energy bands, valence band and conduction band, like normal semiconductor materials. These gallium arsenide and some other semiconductor materials consist of three energy band, and this extra third band is empty at initial stage. So in the next slide we will see three energy bands. That is this is energy level diagram of a Gunn diode. That is, gallium arsenide material consists of valence band, conduction band, and one extra band, that is a higher energy band. And from this energy level diagram we can explain the working. That is, when certain voltage is applied to the device, then electrons in the valence band starts moving towards the conduction band. When voltage is applied, electron starts moving from valence band to conduction band, and thereby allowing a flow of current. As electrons are moving from valence band to conduction band, there is a flow of current. But when the voltage further increases, then instead of allowing a large flow of current, the electrons in the conduction band move towards the energy band present above the conduction band. So after that, electrons moves from this conduction band to the higher energy band. Due to this, the effect is known as a transferred electron effect. So as electron moves from conduction band to higher energy band, this effect is called as a transferred electron effect. And this is so because electrons are transferred from conduction band to higher energy state. At this particular state, as these electrons are less mobile, hence current decreases with the increase in voltage, thereby giving rise to negative resistance phenomena when current decreases with increasing in voltage. When we further increase the voltage from this level, the current decreases again. So in the last, after a certain point of time, when the applied voltage increases further, then electrons in the higher energy band, it is electrons in the higher energy band or energy state, gains sufficient energy and moves back to the lower energy state, that is a valence band. Thus, further the current flowing through the device, the increase with the increase in the applied external potential. Okay, so this is a working principle of the Gunn diode. When voltage is applied, electrons move from valence band to conduction band. There is a flow of current, and further conduction band, electrons again move from conduction band to the higher energy band. And as it gains more energy, electrons again comes to the lower energy band, and from this point the current decreases, and from this point up to this point current increases up to threshold point. So in VI characteristics we will study. So in the VI characteristics, this is a diagram of a VI characteristics of Gunn diode. The current in Gunn diode starts increasing linearly with the applied DC voltage. So this is a forward current starts increasing uh, with the applied voltage. At a particular point, the current starts decreasing. This point is called as a threshold point. So this is a threshold point or peak point. After crossing the threshold point, the current starts decreasing. As shown in this diagram, current starts decreasing and creates negative resistance region in the diode. Due to this negative resistance region, the diode acts as an amplifier. Diode acts as an amplifier and oscillator, and this negative resistance region, the Gunn diode is able to amplify the signal. So Gunn diode, this operates in negative resistance region, and this is important that from this negative resistance, diode acts as an amplifier and oscillator. Okay, so these characteristics are similar to the tunnel diode characteristics, that is forward current increases when will increase the forward voltage up to peak point. Forward current increases after this point, if you will increase the forward voltage, then current starts decreasing, and up to this point this is called as a negative resistance region, and in this negative resistance region diode acts as an amplifier and oscillator. And next is a two-valley model theory of a Gunn diode. So in sometimes exam explain two-valley model theory of a Gunn diode, such type of a question asked, and we have to explain. So consider this diagram. This is a conduction band, this is forbidden band, and this is a valence band. A few years before the Gunn effect was discovered, Cromier proposed a negative mass microwave amplifier. According to energy band theory of then type of gallium arsenide, a high mobility lower valley is separated by energy of 0.36 electron volt. So this energy lower valley is separated by energy of 0.36 electron volt from a low mobility upper valley as shown in this diagram. Okay, so in this two-valley model, observe here carefully. From this diagram, we can explain this two-valley model. In the first, electron densities in the lower and upper valleys remains the same under an equilibrium condition. Under equilibrium conditions, electron densities in lower and upper valley remains same. And second, when the applied electric field is lower than the electric field of the lower valley, that is when E is less than E, as explained here, then no electrons will transfer to the upper value as shown in this diagram. So when E is less than E, then there is no electrons will transfer to the upper valley as shown in this diagram. And third point, when the applied electric field is higher than that of the lower valley, that is when applied electric field is higher than that of lower valley and lower than that of upper valley, that is EE is less than E less than EU, then electron will begin to transfer to the upper valley. So electron will begin to from lower valley to upper valley as shown in this diagram when EE is less than E less than EU. That is when applied electric field is higher than that of a lower valley and lower than that of a upper valley. Then in the fourth case, when the applied electric field is higher than that of a upper valley, that is when EU is less than E. EU is less than E, all the electrons will transfer to the upper valley as shown in this diagram. So all these electrons are transferred to the upper valley. Then next is a difference between micro transistors and TEDs. So in this difference, we will take that is a main points, that is a transistors operate with either junction or gates, but TEDs are fabricated from compound semiconductors such as gallium arsenide. Okay. Then indium phosphide or cadmium telluride. Transistors operate with warm electrons whose energy is not much greater than the thermal energy of electrons in the semiconductor, whereas TEDs operate with the hot electrons whose energy is very much greater than the thermal energy. So as previously mentioned, TEDs, Gunn diode. TEDs are bulk devices having no junction or gates. Transistors operate either junction or gates. TEDs are fabricated from compound semiconductors such as GAS, indium phosphide, cadmium telluride. The majority of transistors are fabricated from elemental semiconductors such as silicon or germanium. TEDs operate with hot electrons, transistors operate with warm electrons. So this is a major difference between TEDs and transistor. Another difference between Gunn and PN junction diode, if you consider in the construction point of view, the Gunn diode, it consists of N-type semiconductor material, and in junction PN junction diode, it consists of P and N type of a semiconducting material. In the Gunn diode, it has a N plus material. No depletion region is formed. It has a P type, N type, and depletion region between these material is formed there. And this is a symbolic representation of a Gunn diode. This is a symbolic representation of a PN junction diode. As if you take the VI characteristics, observe here as previously mentioned, these are the VI characteristics of Gunn diode, and these are the PN junction diode VI characteristics we have already seen. Okay, so this is when forward voltage increases, forward current increases up to the threshold value, then when forward voltage is again increase beyond this threshold value, then forward current starts decreasing. Okay, and this is called as a negative resistance region. And you better know this PN junction diode forward and reverse characteristics. Because of these fundamental differences, the theory and technology of transistors cannot be applied to TEDs or Gunn diode. Okay, the next advantages of Gunn diode: portable and small size device. Cost of manufacturing of Gunn diode is low. It possesses better noise to signal ratio as it is immune from noise disturbance. Gunn diode is reliable and stable at high frequencies. It has a high bandwidth of operation. The manufacturing cost of Gunn diode is very low. It exhibits comparatively low operating voltage than normal diodes. Its installation in circuit is easy. So these are the advantages of Gunn diode. Then disadvantages: the Gunn diode has a poor temperature stability. The device operating current is higher and therefore power dissipation is more. The efficiency of Gunn diode is low, below 10 GHz. These are less stable. efficiency of gun diode is very low. Sometimes noise effects are more in case of a gun diode. So these are the disadvantages. Then gun diode applications, n number of applications in present life, that is electronic oscillators to generate micro frequencies. It can be used as parametric amplifiers, as a pump sources in police radars, as sensors in door opening system. Okay, that is a trespass detecting system, pedestrian safety system, etc. It can be used as a source for micro frequencies in automatic door openers, traffic signal controllers, etc. It can be used in a micro receiver circuit. It can be used as in a radio communication, in military system, in remote vibration detectors, in tachometers, in pulse gun diode generators, in microelectronics as a control equipments, in radar speed guns, as a micro relay data link transmitters, continuous wave Doppler radars. In that, these gun diodes are used. Okay, so in detail we have studied gun diode, that is what is gun effect. Then next is we have seen that is a symbolic representation of gun diode, and construction of gun diode, material used for gun diode, then working principle of a gun diode. Then next we have studied VI characteristic of gun diode. Also we have studied two value model theory of a gun diode. Then we have studied advantages, disadvantages. Then we have also taken major difference between gun diode and PN junction diode or transistor, we can say. Okay, thank you.